No, okay, so what we're going to see here is the factor theorem. And put simply, it's a very important theorem that you're going to need in order to write any polynomial in its fully factored form. Here, we're given a polynomial, and this is a very generic polynomial, p sub n of x, which equals to a times x to the power of n, and there would be an x to the power of n minus 1, x to the power of n minus 2, all the way down to a sub 0 times x to the power of 0. In other words, a constant term. What the factor theorem tells us is if p of c is equal to 0, in other words, if there's a number such that if I replace all the x's by that number, it's equal to 0, then x minus c will be a linear factor of the polynomial. Conversely, if you know that there's a linear factor, x minus c, then if I evaluate the polynomial at x equals to c, it has to be equal to 0. This is the factor theorem, and rather than stating it like this, I'll just give you an immediate example. So here's the deal. Let's say I give you this. P sub 3 of x equals to x cubed minus 7x minus 6. And I should say you don't have to write this p sub 3. I'm simply writing it there to showcase or highlight the fact that I'm dealing with a polynomial of degree 3. Okay, since the highest power of x I see is 3. Now, you can go ahead and check this, but there's a solution, which we sometimes call obvious solution, or in French we'd say solution évidente. Very often in an IB exam, if you need to find the roots, a good idea is to give 1 and negative 1 a shot, right? And I think you'll find that if you replace all the x's inside this by negative 1, what do we get?
0.
Yeah, perfect. If I replace all the x's by negative 1, let's say, in fact, we could quickly do it, that would be equal to negative 1 plus 7 minus 6 equals to 0, right? Are we comfortable with that? What that tells us is that negative 1 is a root. Now, in turn, what the factor theorem tells us, according to this first bullet point here, since the polynomial evaluated at negative 1 is equal to 0, then x minus negative 1, in other words, x plus 1, has to be a linear factor of the polynomial. That's what the factor theorem is telling us. So let me just sort of phrase that. We know that since p of negative 1 equals to 0, what the factor theorem tells us, I'll just write capital F T for factor theorem. The factor theorem implies that x minus negative 1 is a factor. Of course, it's a linear factor. I'm just writing factor to go a bit faster. Now, I'm sure you can appreciate that x minus negative 1 is the same thing as x plus 1. So I'll just write that, i.e. x plus 1 is a factor. Yeah? Now, why is this useful? It's going to become very important on many occasions to write a polynomial as a product of its factors. And when I say factors, ideally linear factors, but sometimes there will also be quadratic factors, but we'll get to that later. Okay? If we're working within the set of complex numbers, as we'll be seeing, if the polynomial has degree n, then there will be n linear factors. It's pretty amazing. It stems from the fundamental theorem of algebra that we'll be learning next week. But for now, what matters is that we've just established that x plus 1 is a factor to the polynomial that we have right here. Consequently, if I were to, by very definition of a factor, if I divide this polynomial by this factor, what should the remainder be?
0.
Yeah, that's the definition of a factor, right? So, let's do that. I'll use synthetic division, and so on the far right hand, or the upper right hand corner here, I'll write, we're going to do x cubed minus 7x minus 6 divided by the linear factor we know is a factor according to the factor theorem. Now for that, we'll use synthetic division. So we set up our table. And the coefficients of the cubic are 1, 0, negative 7, negative 6. And we're going to be dividing by x plus 1. And x plus 1 would be equal to 0 at x equals to negative 1. So I write negative 1 here. Yeah. Now, synthetic division. I carry down the leading coefficient to the bottom of the table, like so. Now, negative 1 times 1 is equal to negative 1. I add the 0 above it, which gives me negative 1. I now repeat that process. Negative 1 times negative 1, that's equal to 1. I add the negative 7 above it, which gives us negative 6. I carry on. Negative 1 times negative 6 gives us 6. I add the negative 6 above it, and I get 0. This is the remainder, capital R, and the fact that it's equal to 0 confirms that x plus 1 is a factor to the polynomial. What matters to us here, though, what's really cool, is that now we can state that our original cubic, x cubed minus 7x minus 6, is equal to the product of x plus 1, that's the factor we had, and the quotient polynomial whose coefficients are right here, right? So capital Q of x, which, well, it's going to be equal to x squared minus x minus 6. So we can now state that x cubed is equal to x plus 1 times x squared minus x minus 6. This is particularly useful because suddenly we've now faced with a way to find all three roots, if there are three real roots, of this cubic polynomial, right? Because I know that negative 1 is a root, and I can now focus on the quadratic that we have here, and we've known how to solve quadratics forever. So x squared minus x minus 6, hopefully you'll appreciate that I could rewrite that as x minus 3 times x plus 2, if I write it in factored form. Yeah? In other words, that's the same thing as x plus 1 times x plus 2, did I say? Times x minus 3. Done. I've now rewritten that cubic in fully factored form, I should say as a product of its linear factors. And that allows me to quickly state that the roots, or the zeros, of x cubed minus 7x minus 6 are 2 dots, x equals to negative 1, x equals to negative 2, and x equals to 3. You can see that I got particularly creative when I came up with this example. Right? Done.